The role of endogenous and exogenous biodiversities in antibiotic resistance mitigation in a context of treated wastewater reuse. So just a little bit of context, we already talked about that yesterday, but water scarcity is one of the major issues of the 21st century due to global warming and demographic boom. It impacts a lot farmers that cannot supply the growing demand anymore, that are undergoing declining yields, lower product quality, and rising costs. And besides all of it, about 17% of the total renewable freshwater resources are being discarded. So to remediate to this issue, several countries have already implemented the reuse of treated wastewater as a means of irrigation of soils and crops. However, we need to be careful with this practice because compared to freshwater, the physicochemical properties are different with higher nitrogen, phosphate, sulfate, organic matter contents. It contains pharmaceutical residues, heavy metals, the bacterial population, so the exogenous bacterial population is different from freshwater and from the endogenous bacterial population, which is the soil bacterial population. It contains also resistant bacteria, pathogens, antibiotic resistant genes, and mobile genetic elements. And all of this could contribute to the dissemination of antibiotic resistance, which is also a main concern of the 21st century. So in this context here, we've tried to answer to 3 questions. Does actually the use of treated wastewater for irrigation really play a role in the dissemination of antimicrobial resistance? Does the soil history corresponding to the type of water used for irrigation play also a role? And what is the part of the soil microbiome in this dissemination? So to do this, we've designed an experimental setup with 2 historical soils. So a tap water soil, which has been irrigated for 1 year with tap water, and a treated wastewater soil, which has been irrigated for 1 year with treated wastewater with a priori viable endogenous bacterial communities. So we've performed the experiments in a soil microcosm. These soils underwent or not an inactivation treatment to reduce the endogenous bacterial diversity, the bacterial community, to know if the exogenous bacterial community from treated wastewater could colonize or not these weakened soils. And finally, we've irrigated this microcosm with either tap water or treated wastewater with variable exogenous bacterial communities. So we've irrigated this microcosm in 1 shot at the beginning of the experiment with the volume corresponding to 1 year of irrigation. So globally, the same amount of water compared to our historical soils, but this time it was in 1 shot, whereas in our historical soils, they were irrigated at different frequencies over the year. And then we've performed physicochemical analysis, qPCR analysis to monitor the bacterial abundance, some antibiotic resistant genes, mobile genetic elements, and we've performed 16S sequencing to monitor the evolution of the bacterial communities. So about the results, I'm first going to focus on the role of irrigation, waters, and the dissemination of antimicrobial resistance, and the characterizations of these waters. So about the exogenous bacterial diversity, we could see that treated wastewater had a higher diversity compared to tap water that was expected with proteobacteria, but also with a considerable proportion of Nitrospirae and Bacteroidetes here. About the key gene abundances, we found globally higher bacterial abundances and higher copy number of antibiotic resistant genes and mobile genetic elements among the selected ones, 2 to 3 log unit higher, and also higher ammonium nitrate and nitrate concentrations in treated wastewater compared to tap water. And there were also the presence of several pharmaceuticals in treated wastewater. So about the results, I'm going to show you the results obtained with the tap water soil, knowing that globally the same trends were observed with the treated wastewater soil. So here you have the evolution of 1 mobile genetic element and 1 antibiotic resistant genes in the soil tap water irrigated in our microcosm with tap water or treated wastewater. And globally, we couldn't see any clear variation of these genes across the time, and no statistical differences were observed between the irrigation type, between tap water and treated wastewater. About the bacterial communities, you can find here a heat map with the 25 most abundant genera in our tap water soil. Here, the incubation time and the irrigation type. And what we could see, it's an evolution of the bacterial communities across the time with here, I represented the evolution with this PCA, the first incubation day, the intermediate incubation days, and the final incubation day, 85 days. So an evolution with, just after irrigation, an enhancement of some here. Nitrifying bacteria in green and xenobiotic degraders, and then a decrease across the time. However, we could not discriminate between the irrigation type here. So it seems that in our experiments, in our microcosm, irrigation waters do not seem to impact the endogenous communities, as no differences were observed. But it could come for our irrigation strategy, which was in one shot, which is different from irrigate at different frequencies, and it could play a role. And effectively, when we compare our historical soils that were irrigated at different frequencies, we could find different bacterial communities. So here you can find the tap water soil and the treated wastewater soil at the initial time. And some genera were actually mainly found in the tap water soils. Some were observed in both soils, and some others were mainly found in treated wastewater soil. And globally, the main change concerned the nitrifying bacteria abundance that were increased in the treated wastewater soil. So in green here, the proportion was globally higher. There were also some sulfate reducer, nitrate reducing bacteria in treated wastewater soil. And about the gene abundance, we found similar abundance between these two soils. But about the physicochemical properties, we found in treated wastewater soils higher concentration of ammonium, nitrate, and sulfate compared to the tap water soil. So finally, in this first set of experiments, we could not see any enhancement of antibiotic-resistant genes or mobile genetic elements in our microcosm and in our historical soil after treated wastewater irrigation or tap water irrigation. But in our historical soils, it seems that the irrigation with treated wastewater induced changes in the soil chemical composition with an increase of nitrogen, sulfate, phosphate concentrations, which may impact the bacterial communities and more specifically nitrifying bacteria. I'm then going to talk just a little bit about the treated soils that underwent an inactivation treatment. And so these soils have been in our microcosm irrigated with treated wastewater. And you can see here the evolution of the bacterial abundance, and here one antibiotic resistant gene. And you have the tap water, the treated wastewater soils, and the same soils with underwent an inactivation treatment, so with a reduced bacterial population. And what we could see is just after irrigation here, an increase of the bacterial abundance and then a decrease across the time with our inactivated soils. And we could see globally the same trend with SUL1 gene, the antibiotic resistant gene. So an increase after irrigation and then a decrease across the time. And I won't show you the result, but globally what we could see after irrigation is an enhancement of the nitrifying bacteria and possible pathogenic bacteria. And here I represented the Euler diagrams of the shared OTUs over the time at 0 days, 1, and 85 days. And just to show you what it shared between treated wastewater soil and treated wastewater soils that underwent inactivation treatment. And what we could see, it's the proportion here of the shared bacteria between treated wastewater and this soil remained quite constant over the time, which means that the increase here of the bacterial abundance which is observed may actually come from the endogenous bacteria that are stimulated by the irrigation, and not from the exogenous bacteria from treated wastewater. And so finally, from these experiments, in our microcosm, irrigation do not seem to promote the selected antibiotic-resistant genes or mobile genetic elements increase, and no significant differences were observed between the irrigation type, even if they were actually different in terms of characterizations. In our historical soils, we could see an increase of the abundance of Nitrophane bacteria in treated wastewater soil compared to tap water soil, an increase also of nitrogen content, but no increase of antibiotic-resistant genes or mobile genetic elements. And in our weakened soils with low bacterial diversity, they seem to be more sensitive to pathogen bacteria developments and denitrifying bacteria developments also. And they were associated with an increase of antibiotic-resistant genes and mobile genetic elements just after irrigation. But irrigation seems only to stimulate endogenous bacteria already present in soils. And so finally, we would need to identify exactly which are the parameters that disturb soil microbiome and resistance. Why do we observe differences between our microcosm and our historical soils? Is it due to irrigation frequency, physico-chemical compositions, or other parameters? And precautionary measures should be taken with low diversity soils that seem to be more sensitive actually to pathogen bacteria, and some more intensive study need to be conducted. So thank you for your attention.
Thank you.